Welcome back. We're looking at section 8.2, the Pythagorean Theorem and its converse. Now, you may already be a little bit familiar with Pythagorean Theorem, that whole a squared plus b squared equals c squared thing, except this time we are going to be adding in the converse. The converse is when you flip the order of your if-then statement and get it to mean something else. And it's this power of being able to take the Pythagorean theorem and kind of think about it in terms of an if-then and flip the order of that will allow us to do something really cool. It'll allow us to classify a triangle as acute, obtuse, or right, knowing just the side lengths. It's really cool, so let's jump in it. Now, the Pythagorean theorem is almost without argument one of the most famous theorems that we have in mathematics. And what it does is it relates the length of the legs of the right triangle to the hypotenuse of the right triangle. Remember, the hypotenuse is always going to be the side that's directly across from the right angle. Now, it says this: if a triangle is a right triangle, with the right angle being at C, then a squared plus b squared equals c squared. Notice our if then. The first part, if our hypothesis is if we have a right triangle, then we can use the formula a squared plus b squared equals c squared. So if we think about the top of the lesson, when we were talking about introducing the converse and flipping it, we can now go, well, if a squared plus b squared equals c squared, then I know my triangle's a right triangle. We'll use that toward the bottom of the lesson. But first, let's practice Pythagorean theorem real quick. So here I have a triangle. It is a right triangle because I see a right angle. And I am going to write out my Pythagorean theorem just so that I have it. A squared plus b squared equals c squared. I have to decide which side is A, which side is B, which side is C. C is always going to be the hypotenuse, and it's always going to be the side directly across from the right angle. Here's my right angle, and so this must be my hypotenuse. The other two sides, one is A and one is B, and to be honest with you, no one cares which one you make A and which one you make B. Just make a choice and then substitute. Everyone is happy. Just make sure you put C as the hypotenuse, and you make the hypotenuse the side that is directly opposite the right angle. Otherwise, this thing breaks. All right, doing my substitution, I have marked that A is the side measure 6. I've marked that B is the side measure 15, and my hypotenuse is side measure X. I don't know. All right, going to simplify. 6 squared is 36. 15 squared is I believe it's 225. All right, 225. And then I'm going to add those together to figure out what x squared is. 225 plus 36 is 261. Now it feels like I'm done, except that the hypotenuse measure is not x squared, it's just x. So I have to get rid of this power of 2 that's sitting there on the x. To undo a square power, you're going to use a square root. So take the square root of both sides, this square root sitting right next to the square power. Those two will cancel each other out, and you're going to be left with, my apologies, just trying to zoom in. You're going to be left with just x when you take the square root of a square power. So x equals the square root of 261. Now the rule for fractions when we were dealing with fractions last chapter was that if our fraction was reducible, we could simplify it. We could write it in lesser terms. If we could simplify the fraction, we must simplify the fraction. The same thing holds true here with radicals. If I can simplify the radical, I must simplify the radical. So I have to go through the hard work of checking to see if I've got any pairs of factors in here. So I'm going to start looking at factors of 261. This is a really big number, and I don't have things memorized that multiply together to give me 261. So I'm going to find my little calculator to help me out. What I'm going to do is I'm going to start dividing 261 by whole numbers, and I'm just going to guess which whole numbers. But I'm going to guess kind of with a little bit of intelligence. I'm going to look at the last number. It's an odd number. It's not even. So I'm not going to divide this thing by any of my even numbers. I'm not going to divide it by 2 or 4 or 6 or 8 because I don't appreciate, because 261 is not an even number. So it will not be divisible by any of the evens. Okay, so my next number then I can use is a 3. So I'm going to divide this by 3. When I divide it by 3, I get a whole number out. So 3 is a factor of 261. My result for my calculator is an 87. Now I'm going to do the same thing, but with 87. The number at the end is an odd number. 7 is odd, which means 87 is not even. So I'm not going to bother trying to divide 87 by any of the even numbers. Not 2, not 4, not 6, not 8, not 10, not any of those. So I'm going to try to divide 87 by 3 again. Ooh, I get another whole number. This time I get 29. So that means that 3 is a factor of 87, and so is 29. All right, I'm going to play the game again with 29. 29, still not even, still not going to divide it by 2. So I'm going to try by 3 again. I've had a lot of luck with 3, and it throws up on me. It gives me a big decimal, so 29 is not divisible by 3. All right, I can't divide it by 4 because 4 is even. And can I divide it by 5? Well, the trick to dividing by 5 is that my number should end in a 0 or a 5. 29 doesn't end in a 0 or 5, so not divisible by 5. Well, maybe it's divisible by 7. I don't know. I'll try it. Nope. Weird decimal. Not divisible by 7. Not divisible by 8. Divisible by 9. No. And I know that without checking, because in order for something to be divisible by 9, it also has to be divisible by 3. And since I checked 3 at the beginning, I don't have to check 9. Okay, we're starting to get pretty big numbers. I feel fairly comfortable that 29 is maybe a prime number. So I'm going to stop here, and I'm going to call these the prime factors of 261. Now, if you want to speed up this whole prime factor thing and get really good at it, just practice. Just sit down a couple minutes a day, work on your multiplication times tables. There might be some nifty games on the internet that you can play that allow you to practice your multiplication. And it's just to help you see patterns. Again, you can always use your calculator as well to help you with those divisions. All right, thinking back to what square roots want. Square roots want pairs of things. I have a pair of 3s, so I'm going to write 3. And I don't have any more pairs in there, so I have the 29 by itself. So I'm going to write the square root with the 29 inside, because that's what's left over after these two 3s hook up and go out on a date. That is the exact measure of the hypotenuse of this triangle. Now things get a little more complicated when you're given the information for the hypotenuse like we have in this particular example, and you've been asked to calculate the measure of one of the sides. So let's go ahead and run that together real quick. I'm gonna start with my formula, a squared plus b squared equals c squared. Remember that the only one that's important for you to get into the correct place is the hypotenuse. That always has to be in the position of C. A and B can literally be any of the two legs that you want it to be. All right, there we go. Gonna go ahead and substitute. I have 9 for A. I have X for B. And I have 11 for C. All right, just zooming in nice and tight so you can see my handwriting. 9 squared is the same as 9 times 9, which is 81. I don't know what x squared is, so I'm going to leave it as x squared. 11 squared is 11 times 11, or 121. Now I have to get rid of the 81 first before I can get to the x. So I need to subtract both sides by 81. This side cancels, leaves me with x squared equals whatever 121 minus 81 is. Let me do it in my calculator real quick. 40. All right, so I need to find the square root of 40. Why square root? Because I want x by itself. And right now, x is not by itself. X is sitting with x squared. So x equals the square root of 40. I need to check to see if this can be simplified, because if I can simplify it, I must simplify it. No, I do not want you to give me decimals in this section. I really want you to practice this reducing, simplifying radicals. So to simplify the radical, once again, we're going to try to find the prime factors of 40. I can get to 40 as 2 times 20. 2 is a prime number. I'm going to think of 20 as 2 times 10. And 10 I'm going to think of as 2 times 5. All right, so here is my prime factors of 40. So I'm going to write those all under the radical just to make it easier for myself to see where the pairs are. Okay, there's all my factors. And I see a pair of 2, so I'm going to go ahead and write that 2 down. And I don't have any more pairs, and so for my response, I'm going to write square root. And then these 2, I'm going to multiply them together to give me a single value. So the exact value of this leg of my right triangle, this one right here, is 2 square roots of 10. Awesome. We remember how to use the Pythagorean theorem. But we talked about at the very beginning of this lesson that we could use this whole a squared plus b squared equals c squared Pythagorean theorem craziness to classify. Before we classify, I want to give you a shortcut. This shortcut is called the Pythagorean triple. The Pythagorean triple is just a set or a group of 3 non-zero whole numbers that make the Pythagorean theorem true, that fill in the a squared plus b squared equals c squared equation. You write it as an extended ratio, that same extended ratio that we had studied back in chapter 7. Here are the most common Pythagorean triples, and I highly recommend that you make sure these are in your notes. So that way, when I put something on a test like this, we want to use a Pythagorean triple in order to find our missing side. All right, so if I look at this triangle, I notice that the hypotenuse is 13, one of the legs is 12, and I'm missing the other leg information. Well, if I look at my table, the largest number in each of this set of triples is always going to be my hypotenuse. Well, looking at my triangle, Hypotenuse is 13, so maybe it's this one. The leg I've been given information for is 12, which I have, which means that my missing leg measurement is 5. It's 5 because 13 and 12 are the other two numbers in this particular Pythagorean triple. Let's practice so you can see just how easy this is. I'm going to look at 2A. All right, I've got legs of 20 and 48. So I'm going to look at my table at the smaller two numbers and try to find 20 and 40. I don't have that. But what I do have is this extended ratio. Do you notice these extended ratios? So I can try to find some sort of relationship with the numbers I've been given to the Pythagorean triples in this extended ratio kind of feel. All right, so what I'm going to do is I'm going to think about 20 as, it's the smallest side. 20 is not divisible by 3, so it can't be this one. But 20 is divisible by 5, so maybe it's this one. So I'm going to think of 20 as 5 times 4. All right, if it is this particular triple, then the next biggest side is going to be 12 times something. So 48. Is 48 divisible by 12? I take my calculator and I do 48 divided by 12, I get 4. Yo, check it out. Both of these sides got multiplied by 4. Notice how this had a multiply by some number, and it was the same number across that entire extended ratio. So if that number is 4, then it becomes 5 times 4, 20. 12 times 4, 48. And my hypotenuse then is 13 times 4, whatever that is. So this side is 13 times 4. Into my calculator, and 13 times 4 is 52. So this side measure is 52. This is a shortcut to the Pythagorean theorem, and as long as you write out for me, I used a Pythagorean triple. If you see the pattern, you can use this. Otherwise, you have to do all of this and show me all this algebra. Your choice. Okay, now that we have a shortcut, let's talk about the converse, because really, this is the coolest way to use the Pythagorean theorem. It starts off with theorem 8.5, the converse of the Pythagorean theorem, that says that if I take the two legs of a triangle, square them, and then add them, I should get exactly the same thing as the length of the longest leg squared. If that setup is true, then I can say that the triangle I've been given is a right triangle. If I want to classify it as an acute triangle, what happens is that the biggest side of my triangle, squared, needs to be smaller than the other two sides, squared and added together. To make it an obtuse triangle, you're going to look at that longest side, squared, and have that result be bigger than the other two sides, squared and added together. Let's practice. So we want to determine if the triangle with these three side lengths is acute, right, or obtuse. First thing to do is, can these be a triangle? Because if these can't make a triangle, then I basically don't have to do anything else. I can't classify it, because if it's not a triangle, it can't be an acute triangle. So I need to go back to look at the triangle inequality theorem from chapter 4. And I'm going back to my notes just to find it, and I believe it was in section what? Not 4.2. Was it in 4.3? No. The third angles theorem. I don't always have these memorized, so it is completely okay that you don't, but you do have to go back into your notes to look. It wasn't in chapter 4. Was it in chapter 5? Flipping through chapter 5, and I'm looking for the triangle inequality theorem. Oh, here it is. It was in section 5.5, and it says the triangle inequality theorem. Hopefully that was in frame. And so basically what it says is if I take two sides of the triangle, add them together, it should be bigger than the third side that I didn't add. I'm going to do that for all the different combinations. Okay, so I'm going to do 7 plus 14. Yep, that's bigger than 16. I'm going to take 7 plus 16. Is that bigger than 14? Yep. And then I'm going to do 14 plus 16. Is that bigger than 7? Yep. Okay, so this thing totally gets to be a triangle, and so I can classify this as either acute, obtuse, or right. Awesome. In order to make that classification, I have to use that Pythagorean theorem converse. I'm going to compare the square of the longest side, that's this, with the sum of the squares of the other two sides and see what kind of relationship I get. So I'm going to call this C, and these can be A or B in no particular order. All right, so I want to look at C squared. C squared is 16 squared, and 16 squared is 256. All right, and now I'm going to look at the sums of the squares of the other two sides. That's A squared plus B squared. A was 7. B was 14. 7 squared is 49. 14 squared is 196. And 49 plus 196, 245. All right, I'm going to compare these two values. Which one is bigger? C squared is bigger. Now, looking back up at my theorems, when C squared is bigger, the triangle is obtuse. So this triangle is an obtuse triangle because C squared was bigger than A squared plus B squared. The square of the longest side was bigger than the sum of the squares of the other two sides. That's how you use the Pythagorean theorem's converse to classify triangles. I first have to check to make sure that the 3 measurements I've been given will actually make a triangle. Then I find the biggest side and square it. Then I take the other two sides, square each of those, add them together, and then I compare. If C squared is bigger, the triangle's obtuse. If C squared is smaller, the triangle's acute. If they're equal, it's a right triangle. That's all I had for this section for you. Thank you so much for joining me again here today. If you've got any questions, please feel free to leave those in the comments. As always, please don't forget to like and subscribe. And if you're in my class this year, ring that notification bell so that you can see when I've posted this lecture and you can run and find it. Thanks again, and we'll see you next time. Bye.